Okay, in this segment, we're going to try to get at the form of the ideal diode equation. And if you recall, this was introduced on the pre-lab 2, and it was basically that the current through the ideal diode is going to be some saturation current, I sub s, times e to the v over ut minus 1. So here Is is the saturation current. Ut is the thermal voltage. Which is the Boltzmann constant times the absolute temperature in Kelvin divided by the charge on an electron. And this is typically like 100 femtoamps or so. And this is at room temperature, it's about 25 millivolts at 300 Kelvin. It's like 25.8 or something like that. 25 is a nice round number because 1 over 25 is 40. And here I is the current through the diode, and V is the voltage across the diode. So we have diode, which is typically shown like that, and we have some voltage across it like this, and some current flowing through it like this. Okay. And we're going to try to get at the form of this equation. Okay, where does this e to the minus v over ut minus 1 come from? We're not going to be so concerned with exactly what's inside this this is parameter, and I'll say more about that a little bit later. But for our purposes, we're interested in sort of painting with broad brushstrokes and trying to get at where this factor comes from that determines the voltage, the current voltage relationship. You'll notice that when V is positive, very quickly the exponential, so when V is greater than, let's say, I don't know, 4 thermal voltages, e to the v over ut is greater than e to the 4, which is about 100, and that is much greater than 1. And so I is just approximately given by I sub s e to the v over ut, and we can ignore the 1. And that's often what we're going to do, is to ignore that 1. When v is less than 4 thermal voltages, then e to the v over ut very rapidly becomes much smaller than, well, let's say minus, less than minus 4 ut. E to the v over ut is less than e to the minus 4, which is about 1 over 100, which is much less than 1. And so I is approximately just minus I sub s. And this is the so-called reverse junction leakage. Current. And at the end of last time, we suggested that this was a function of thermal generation events in and around the depletion region, and those electron-hole pairs being swept apart by the enhanced electric field created by the reverse bias condition on the junction. And so these are sort of approximate limiting cases of this ideal diode equation under forward bias conditions. So this is forward biased. And this is the limiting condition under reverse bias. Okay? Of course, when V is within this window of plus or minus 4 thermal voltages, which is incidentally about 0.1 volts, and this is about minus 0.1 volts, a tenth of a volt. So when it's within that band of plus or minus a tenth of a volt, around 0, then you do have to think about the minus 1. But when you're outside of that band, very rapidly that exponential term either becomes very much bigger than 1 or very much smaller than 1, and you can ignore one term or the other. Okay, so we're going to need to define some terms. So we're going to talk about majority carriers and minority carriers. So majority carriers are electrons in the N region, or holes in the P region. Minority carriers are going to be holes in the holes in the N region, or electrons in the P region. So there are not 0 holes in the N region, and there are not 0 electrons in the P region. It turns out that there are many fewer holes in the N region than there are electrons, and certainly there are also many fewer holes in the N region than there would be in the intrinsic case, but they're not 0. Similarly, that there are not 0 electrons in the P region, and those turn out to be critical for the way the diode works. It turns out that the current is going to be proportional to the total excess minority carriers in either the N region or the P region. It's actually the sum of the two. And so let's kind of see how these things work. Okay, so majority carrier concentrations. So for electrons in the N region, we denote that concentration by N sub N. So this is the carrier, and this is the region. And that's going to be approximately constant in that region as a function of position, and it's given by approximately N sub D, which was, as you'll recall, the donor concentration. These are the impurities that donate that extra valence electron to the cause of conducting a current. And at room temperature, we basically make the assumption that all of those donors are ionized, and so that this concentration of mobile electrons is just about equal to the concentration of donors. And likewise for holes in the P region, we denote that by P sub P. Again, this P denotes the carrier type in concentration, and this subscript denotes the region. And this is going to be approximately constant again, and this is N sub A, the acceptor concentration. Okay? And so in equilibrium, minority carrier concentrations, would be given by something like this. So we have holes in the N region. So we denote that by P sub N. And as a function of position, this is approximately just a constant, P sub N0. And this is really, by the Boltzmann distribution, P sub P times e to the minus the built-in barrier height over u sub t. Okay, so if you recall, we have our p-n junction here with a junction boundary. This is p minus and n, and we've got our depletion regions here. And we've got here maybe no bias. So we'll draw that as like a short across the junction. And if you look at the potential as a function of position, you have this thing that looks sort of like this. And then there's this built-in barrier, psi 0, the built-in potential. And so we have some hole concentration over here, and we've got this barrier, which is down for the holes, which is kind of weird. But the hole concentration over here in the N region would be given by the hole concentration in the P region times e to the minus this barrier height over the thermal voltage. That was the Boltzmann thing. So this is the Boltzmann. Distribution. And so because P sub P is about N sub A, we can write this as about N sub A times e to the minus psi 0 over ut. And for the electrons in the P region, we denote that by N sub P. And this is, again, an equilibrium approximately constant, which we could call N sub P0. And that's equal to N sub N, e to the minus psi 0 over ut. Again, the same Boltzmann factor here. And that gives us N sub D e to the minus psi 0 over ut. Okay, so now what we're going to do is we're going to imagine that we have a situation where we are applying a bias here of V, and that's going to reduce this barrier so that it's lower than the built-in potential. So it's going to narrow the depletion region a bit. And so we're going to have something that looks maybe like this, where our barrier is now psi 0 minus the applied bias V. And so what we're going to find is that let's think about the N sub P at the edge of, so let's plot this. So we call this N sub P, and this is NP0, the equilibrium concentration. What we're going to find is that there's going to be an increase in N sub P right there at the edge of the depletion region, which we could call x equals 0. And that's going to be equal to, again, n sub d, that's n sub n, really, the majority carrier concentration in the n region times e to the minus the barrier height. Well, now the barrier height is psi 0 minus v over ut. And it turns out that sets a boundary condition, and these excess minority carriers then start to recombine with the holes in this region, and we get basically an exponential decay as a function of position back to the equilibrium concentration. If we get far enough back here into the P region, we get back to that NP0. Okay? And it turns out that the area of this between this exponential curve and NP0, that's called the excess minority carrier concentration. So that's going to be delta n sub p, which is the excess minority carrier concentration. And that's terrible. So let's see if I can draw this up. This thing is delta n sub p, and that's the excess, so-called excess minority carrier concentration. And it turns out that the current is going to be proportional to the area under this curve, divided by either like a half-life or a transit time, how long it takes the carrier to kind of get to the contact, that kind of thing. So it's this total amount of charge divided by sort of a average amount of time that charge lives in the region before it gets recombined, or for the case of a contact very close to the junction, the depletion region edge, it turns out to be more like an average amount of time it takes the carrier to get from the edge of the junction to the contact. But in any event, it's really the area under this curve, which in turn actually turns out to be, under a wide range of conditions, proportional to how far above NP0 this boundary condition winds up being. And so delta n sub p of 0 would be equal to NP of 0 minus NP0. And that's equal to n sub d e to the minus psi 0 minus v over ut minus what NP0 was, which was n sub d e to the minus psi 0 over ut. And of course we can take this e to the minus psi 0 plus v over ut and break it up into a product of two things and factor out the common stuff. And this is equal to n sub d e to the minus psi 0 over ut times the quantity e to the v over ut minus 1. And so here is that factor that we found in the ideal diode equation. Okay, so similarly, we would find that there is, for the p side, there's a p sub n as a function of position, and there's a equilibrium concentration p sub n0, and there would be a, again, exponential type of decay from that injected amount of carriers at the junction edge, and this would be delta p sub n. Delta p n of 0 is going to be basically n sub a times e to the minus psi 0 over ut times the same factor, e to the v over ut minus 1. And so it turns out that the current, so the electron current, is proportional to this delta np0, and the hole current is proportional to delta pn0, and the total current, I, is equal to the sum of the electron current plus the hole current. So the electrons are moving this way, so the electron current and the holes are moving this way. So the hole current is moving from P to N, the electron current is moving from N to P, but since the electrons have a negative charge, the electron current under conventional current flow is going in the same direction and adding to the hole current. And so since all of these factors are proportional to this e to the v over ut minus 1, the whole thing is going to be proportional to e to the v over ut minus 1. And we just call the constant proportionality I sub s. So it's a current, has units of amps. It has to in order to make the units work out. And it has a whole bunch of stuff in it. It's got diffusion constant for holes and electrons, and it's got the donor concentration, the acceptor concentration. It's got this exponential factor with the built-in potential in it. And in some sense, for our purposes, I don't really care what all's inside it. The details don't matter about what's inside it because, first of all, we're making all kinds of assumptions about the physical structure here that are idealizations, like, for instance, the uniform concentration of acceptors and the uniform concentration of donors, and we're making an assumption that we have what's called an abrupt junction, where you basically have a very sharp boundary between the N region and the P region. Like we have these two chunks of material with a perfect edge and we slap them together with some kind of ideal glue. Well, that's not really a realistic situation. The way these things are actually made is that you have kind of what's more like a graded junction where there's a gradual changeover between the N and P. And so that's what's preserved if you do a more realistic model is this sort of exponential factor here. The exponential dependence of the voltage is something that actually is preserved over a wide range of different sorts of assumptions about the physical structure. But what's inside here, what's inside the prefactor, is something that does change some. And the other thing to note is that here, because of this e to the minus psi 0 over ut, if you have the temperature change by an appreciable amount, like for instance over the military specification of temperature range, which is like minus 50 Celsius to plus 100 Celsius, this IS parameter will change by approximately a factor of 1,000,000 over that temperature range. So this is a very exquisite temperature dependence. And so we shouldn't need to know what this is if we have a prayer of making any kind of circuits that are robust to temperature variations. And so we're never in practice going to actually need to know what IS is in detail. I mean, we may do the kind of measurement and curve fit that you're doing in Lab 2, and you may be able to extract it from that curve fitting exercise, and that's all well and good, but we're never going to need to rely on a specific value of IS. And if you were to take a transistor or a diode, and you were to take a measurement, and then you were to blow on it with a hairdryer or a heat gun and repeat the measurement, you would find the curve has shifted by quite a bit. And so, you don't want to be relying on a specific value of IS in your circuits. And we'll look at how it is that we can actually design circuits with elements that have such a strong temperature dependence that are actually robust in their behavior to changes in temperature. Okay, but that's kind of a cartoon picture of where the ideal diode equation comes from. It's a little bit sketchy, a little bit rough and ready. Hopefully it'll fit the bill for this class. I can probably scare up a more detailed derivation if anyone's interested in a little more of the details, dotting all the I's and crossing all the T's. But for our purposes, I think that'll be good. So we'll see you next time.